Hello everyone. In today's lesson, we're going to be looking at how to use the p-value or probability value to test a hypothesis. So the p-value or probability value of a test is the probability of drawing a random sample whose standardized test statistic is at least as contrary to the claim in the null hypothesis. And this is what we're going to be using to test our hypotheses. So to begin with, we'll first start with some random null hypothesis. Let's say that we have h0 mu is equal to, and I'll just pick some value, let's say 64. And we're checking the alternate hypothesis that mu is not equal to 64. And in this case, what we could do with the critical region method that we looked at previously. The problem with the critical region method, though, is all it really tells us is based on our p-value, we're going to have two rejection regions if it's two-tail like this, one on the left, one on the right, and we're looking at, does our test statistic fall into this region, which would make it fail to reject, or does it fall into one of these regions, which would tell us that we have enough evidence to reject our null hypothesis at that level of significance, whatever we chose. Let's say alpha equals 0.05. But this really doesn't give us much extra information. So we're actually going to be using the p-value to give us a better idea of not only whether we reject the null hypothesis, but how extreme or improbable is this outcome that we got if the null hypothesis, in this case mu equals 64, were true. So our p-value, or attained significance, is the smallest level of significance for which the observed data indicate that the null hypothesis should be rejected. Now, as statisticians, what we usually do is we will set some alpha or level of significance at the beginning of our hypothesis test, and then we will test based on our sample data that we took. But a lot of places, what people actually will do is they will just find the p-value and it will tell them at what level you would have been able to reject the null hypothesis. So an example of this might be for if you're using R or Excel or Python or some other program, they generally are going to give you p-values even without requesting them. Like if I were to create some model, let's say a linear model in R, if I do a summary on it, it will then tell me all of my parameters and what their p-value is. It's testing their significance. And it might say something like less than 0.001 or less than 0.05. But as statisticians, we generally want to go into a hypothesis test with some test in mind, some level of significance. And if we fail to reject our null hypothesis, but we still believe it's true, what we would then need to do is we would then need to gather more data, and possibly at that point, we could use a different level of significance. And this can actually lead into one of the bigger issues in science, research, things like that, which is called p-hacking, which I might talk about at another point. So the smaller your p-value is, the more compelling the evidence is in favor of your alternate hypothesis. Because remember, the whole point of a hypothesis test is that this alternate hypothesis is what we actually believe is true. And we're trying to see, assuming that the null hypothesis is true, does our data seem to give us enough evidence to refute this initial claim? So what does this actually mean then? Well, basically what we're doing is we're saying that if we have some distribution which is centered around our null hypothesis, because again, we're assuming that this is true. So we'll say mu is equal to 64. And let's say our test statistic is somewhere out here. Then we're looking at what is the probability that we would get a value that is as far out as this test statistic or further. Now, if we're doing a two-tailed test, we need to consider that we also have to look at the probability of something occurring equally on the left side. And I'll talk more about that in a minute. But first, let's talk about what are the actual decisions that you make. You found your p-value, now what? So what we're going to do is we're going to be comparing our p-value to our level of significance alpha. And there's two different outcomes that we would expect. We're either going to have that our p-value is less than or equal to alpha, or our p-value is greater than alpha. And what this means is that if we have a p-value that is less than alpha, meaning that it is smaller, so let's say that our alpha is here, this actually tells us that we can reject the null hypothesis, and will actually have a probability associated with it to give us how much strength and evidence we have to reject that null hypothesis. So if our p-value is less than or equal to alpha, we will reject the null hypothesis. And if our p-value is greater than alpha, we would fail to reject our null hypothesis. Now, if you're trying to remember this, for example, when you're doing a test, something like that, one little trick that I always teach my students is to think of P as pond, right? So if I have a pond, this is my pond, and I have a fish, right? Because alpha kind of looks like a fish. If my fish is bigger than the pond, it doesn't make sense. Therefore, we need to reject it. If my pond is bigger than the fish, it makes perfect sense for the fish to live in the pond. Therefore, we fail to reject it, right? We don't have enough evidence to reject our null hypothesis. And remember when we talked about our types of error, just because we reject a null hypothesis does not mean that our alternate hypothesis is true. It doesn't even mean that our null hypothesis is wrong. If we fail to reject a null hypothesis, it does not mean that the null hypothesis is true or that our alternate hypothesis is wrong. This is where the types of error come in, right? We use the example of a courtroom. We assume innocent until proven guilty. That doesn't mean whether they committed the crime or not just because they were found innocent or guilty. It just means that there was enough evidence to point to them being guilty, or there was not enough evidence to point to them being guilty. So in this case, it actually isn't telling us directly whether the person is or is not guilty. It's just pointing to where the evidence is indicating whether they were in fact guilty or not guilty. And the reason I bring up this example oftentimes is because with something like that, there's always going to be that certain amount of unknown. And we know for a fact that there are people who are innocent who are found guilty. There are people who later on are found to be guilty that were originally found innocent. And it also gives us a really good indication of why our level of significance is so important, because there are very real repercussions to both decisions. Either more innocent people will end up being imprisoned, or more people who committed crimes will not be sent to prison when they've been caught. So therefore, we have to decide which one of these is more important, keeping innocent people out of prison or making sure that we catch everyone who commits crimes. Next, we're going to look at how do we actually find these p-values using both standard normal and student's t-distribution. But before we do that, let's talk a little bit about what does our p-value actually mean when we find our value. So if you get a p-value that is less than 0.01, this would be considered overwhelming evidence to reject your null hypothesis. If you get a p-value that's between 0.01 and 0.05, this indicates you have strong evidence to reject your null hypothesis. If we have a p-value between 0.05 and 0.1, this gives us some or weak evidence to reject the null hypothesis. And anything greater than 0.10 is generally considered that we don't have enough evidence to reject the null hypothesis. What we're going to do is we're going to look at 3 cases for finding p-value. The first, I'm going to start with the simplest one, which is when we are doing a right tail test. So this means that we have some value, right? Our data is centered at 0 because we're on the standard normal, right? We took our normal distribution and we standardized it. We have some alpha, which represents the area to the right where our rejection region is. And if we get a test statistic, let's say our test statistic is right here, how do we figure out what the probability is to the outside? Well, the fact is we're taking from some point our test statistic and we're looking to the right. So this is going to be the probability that z is greater than, because we want it to the right, our test statistic. So whatever this value is. And then because in this class, I've been giving you all a table that is positive z values looking to the left, what we would need to do is we would need to just convert this really quickly so that we can use this table. If you have a table that has positive z values looking to the right, you could just directly look up this probability right now. But for us, what we'll be doing is this will be 1 minus the probability that z is less than or equal to our test statistic. Or actually, we could have the equals on the other side. It really isn't important because when we have a continuous distribution, the probability of some outcome being equal to is infinitesimally small. So in the end, this really doesn't make a lot of difference. But Some people might actually point out that I probably should have put it here because technically if it's at test statistic. Anyway, so this would be our probability, right? Our p-value, because we were looking at the probability to the right of this test statistic. And then so what we did is we found the complement, which is probability to the left of this test statistic, and subtracted that from 1, and we'll be left with just what's here. So now let's look at what if we're doing a left tail test. So if we're doing a left tail test, same idea. We have some rejection region over here, which is based on alpha, and if we have some negative test statistic that's over here, I'm going to call this negative test, even though it's just our test statistic. I'm putting a negative there to signify that it's a negative value. And this is centered at 0 because we're using standard normal. Now, if we were doing this and we wanted to know the probability that is more extreme, meaning to the left in this case, we're going to first set it up where we have the probability that z is less than our negative test statistic. We're going to, again, if you have a table that has negative values to the left, you could just directly look up this probability. But first, what we're going to do is we're going to convert it to the table that I've been using by first using symmetry to bring it to the positive. So we're kind of saying this, okay, but what if I had the positive test statistic, and I'll look at this area. So this is going to be the probability z is greater than the positive test statistic. And then again, because my table doesn't give me probabilities to the right of a positive z value, I would then just take the complement and I would get 1 minus the probability z is less than the test statistic. Next, we're going to look at a two-tailed test. So we have our standard normal probability distribution. And in this case, we have two rejection regions, which have an area of alpha over 2. Now, we can actually reject our null hypothesis in two ways. We could either have a negative test statistic on the left, and we're finding the probability more extreme than that, or we could have a positive test statistic to the right, and we're looking at the probability to the right of that. So if I were to write out this probability, because it's an or statement, or in probability means that we're going to add them. And of course, they're mutually exclusive. You can't be over here and also be over here. So in this case, it's going to be the probability that z is less than our negative test statistic plus the probability that z is greater than our positive test statistic. So first thing I'm going to do now is for this negative one, I'm going to flip it by symmetry to get it to the right side. So this just becomes the probability of z is greater than our positive test statistic plus probability of z is greater than our positive test statistic. Now you may notice these are the same thing. So what now we're going to do is we're just going to rewrite this as 2 times the probability z is greater than our positive test statistic. And then, of course, to get it in terms that we have where we can use our table, because I don't have probabilities to the right, what we're going to do now is we're going to take 1 minus, we're going to use the complement, and this is going to become 2 times 1 minus the probability z is less than our positive test statistic. So now what I want to do is I want to just put this all together so that you have an easier way to remember this whole thing. So if we have a right tail test, we said that we had the probability that z is greater than our test statistic. For a left tail test, we ended up with the probability that z was greater than the positive test statistic. So if you kind of look at it, they actually end up being the same thing. But what we're going to do is we're just going to say that it's the absolute value of our test statistic. So we don't really care whether it's positive or negative, because if it's on the negative, we can flip it to the positive and it ends up being the same probability. And then if we're doing a two-tail, it ends up being the same thing. Probability z is greater than the absolute value of our test statistic times 2. So really you only have to remember one formula for all of your p-values. It's just the only difference is if it's one tail, you're just doing probability of z greater than the absolute value of the test statistic. And if it's two tail, you take that value and you multiply it by 2. And then I guess, again, if we wanted it in the form that we use based on our table, then this would just be 1 minus the probability z is less than the absolute value of our test statistic. And this would end up being 2 times 1 minus the probability z is less than our test statistic. And that's it. That's all you have to remember in order to do these p-value calculations for standard normal z. Next, we're going to look at how do we find p-value for the student's t-distribution. Now, based on the tool that we have, which is this table, we are a little bit more limited because we don't have as many probabilities associated with each student t-distribution. Because while on the z-table, we only have one standard normal, it means that we can have a more precise probability, whereas with the t, we have to consider a couple things, whether it's one tail or two tail, how many degrees of freedom there are, and also what our test statistic is. So therefore, what's going to happen is we're actually going to get a range of p-values. So first thing we need to do whenever we're doing a student's t-distribution p-value is we need to take the absolute value of our test statistic. So we're going to get the absolute value of our test statistic because our table only gives us positive values. But just like with the standard normal, because of symmetry, if we have a negative value and we're looking to the left, it's the same as a positive value looking to the right. Next thing we're going to do is we're going to look at this table, and if you look at the top, you'll see that it says two tail. If you look at the second row, this says one tail. So this is going to tell you which of the rows you're using to figure out what alpha levels you're between. For your t-value, you are then going to go down to the degrees of freedom, which if you remember for students' t-distribution is n-1, and then you will go across that row until you find the two values that your test statistic falls between. And then from there, you'll go up, and if it's one tail, you will stop at this row. If it is two tail, you will stop at the top row. And that will give you the interval that your p-value falls into. Now, the problem with this interval, let's say we have something like this, that our p-value is between 0.01 and 0.02. We don't know where our p-value is in this interval. All we know is that it's something greater than 0.01 and less than 0.02. It could be 0.01000001. It could be just under 0.02. It could be in the center. We don't know where it is. So this actually leads to a certain ambiguous area that we can't really make a definitive decision on depending on what we get. Now, one other thing I also want to point out about the tool, and this is where I see a lot of students kind of run into an issue, is if you look at this t-table, what's happening is as you go from left to right, we have our levels of significance or our levels for our p-value in descending order. But generally when we write them in ascending order. We do the lowest value, less than p, less than the bigger value. So it's one thing to be careful about. Whatever values you have, you just want to make sure to switch them if you want to write it in this form. Now, just like before, when we were doing the p-value for standard normal, we're still going to compare this to our level of significance that was selected for our hypothesis test. So I'm going to use these values for now, just for the sake of keeping it the same. So let's say that our p-value is between 0.01 and 0.02. Well, if my alpha is larger than this, let's say that alpha is 0.05. So 0.05 would be bigger than the biggest possible value that we can get for this p-value, because our p-value has to be something less than 0.02, meaning that our p-value is smaller than alpha. This would mean that we would reject our null hypothesis. If we have a small p-value, let's say that we have 0.01, if we have a small alpha, let's say that alpha is equal to 0.01. Well, in this case, because my p-value, right here it says, p-value is greater than 0.01, meaning no matter what p-value I have, where it is in this interval, it has to be greater than alpha. In this case, we would fail to reject our null hypothesis. And then the last case is, what if you have kind of a weird situation? Let's say we have 0.01 is less than p is less than 0.02. And my alpha is 0.15, which falls right in this interval. Well, again, because I don't know where my p-value actually is using this table, I can't really say whether my p-value is greater than or less than, right? Because if my p-value is 0.011, it's less than. If my p-value is 0.19, it's greater than. So in this case, my p-value could be either. Because we don't actually know the specific p-value, again, using this tool, this means that this would be inconclusive. So we have to kind of err on the side of caution and just say we do not have enough evidence to reject the null hypothesis. Because remember, we want to set sort of a hard threshold for that. So if it's ambiguous, we got to go with the side that we don't have enough evidence. If we had stronger evidence, then maybe our p-value would actually be smaller and therefore it would support our case. But in this case, we would just have to stick with fail to reject. Now, one last thing I want to talk about this before we move on is that, again, a lot of these shortcomings are because of the tool that we're using. It's because of this student's t-table. If you're finding your t-value, your test statistic, and your p-value for student's t-distribution using a program like R or something like that, you're going to probably get a very precise p-value. And therefore, you would be able to then make that decision. But based on the fact that we're using this table, which is a limited tool with a lot of restrictions, then we're kind of limited in that regard. So let's look at two quick examples to see exactly how we would do this. So let's say that you have some test statistic, t equals negative 2.32. So the first step is we need to find the absolute value of this, and this will end up being positive 2.32. If we're doing a left tail test, and we have an alpha of 0.05, and we have a sample size n equals 5. In this case, if we have a sample size of n equals 5, this means that our degrees of freedom is going to be equal to n minus 1 or 5 minus 1, which means 4. So because we're doing a left tail test, this is a one tail test. So we're going to go down to our degrees of freedom, which in this case I said was 4. We're going to go over until we find the interval that 2.32 falls between, which is these two values right here, 2.1318 and 2.7764. I'm going to go up to the top row, which is our one tail, and I'm going to get 0.0500 and 0.0250. So again, I'm going to flip them. So I get that this is 0.025 is less than p is less than 0.05. And this is what I would compare to my alpha if I were trying to make a decision whether to reject or fail to reject. Or if I just wanted to make a statement about this, this p-value indicates that I have enough evidence to reject a null hypothesis that at less than a 0.05 level, right? Because my p-value, no matter which of these values it is in this interval, is going to be less than 0.05. The next example, we have test statistic is equal to 3.9. And in this case, we're doing a two-tail hypothesis test. We have an n of 6, which means that we have a degrees of freedom of 5. So again, we're going to go on to our table. We're going to go down to 5 for degrees of freedom. We're going to go over until we find 3.9, or the interval that 3.9 falls in, which is right here, between 3.3649 and 4.0321. We will go up to the second row, which is for two-tail test. And on the left side, I have 0.0200, and on the right side, I have 0.0100. So again, I'm going to flip them, which means that we have a p-value of 0.01 is less than p is less than 0.02. This means that we can reject our null hypothesis, based on this example, at a level under 0.02. And then looking at this slide, you can see exactly what I did to find this on our table. The first example, we had degrees of freedom 4. We went over and found the interval it fell into, and we went up to the first row, which represents the one-tail test. For the second example, we had degrees of freedom 5. We went over to the interval that it fell between, and then we went up to the second row, which represents the values for a two-tail test. Let's do two examples to try this out. Now we're going back to the examples we did if you watch the previous videos that I've done on hypothesis testing, and we're now going to add in our p-value component. So just to kind of keep it thorough, I'm going to start from the beginning and do the entire problem. So the first problem states, an SAT tutoring center claims that the average math scores of their students on the SAT is 500. Consider a small sample of 20 students. The sample mean of their scores is 521.5. Previous records show that standard deviation is 120.5. At the 5% level of significance, do you have sufficient evidence to prove the average math score on the SAT is different from 500? Starting this, we have to consider what is our given information. So first things first, we have a small sample of n equals 20 students. We have a sample mean of x bar equals 521.5. We have a known from previous data, meaning we didn't calculate it ourselves, standard deviation, meaning it's sigma, which is equal to 120.5. And then we're testing this at an alpha equals 0.05 level of significance. Now we're going to write our hypotheses. Well, our null hypothesis is the initial claim that the SAT Center made, which is that their math scores on average are 500. And we said that we wanted to see if there's evidence to prove that this is not correct, that it's different from this. Meaning that we're not saying it's greater than, we're not saying it's less than, we're saying that it is not equal to. Now, before we actually go on to finding the values to test this hypothesis, what we need to do first now is we need to check our assumptions. So our assumptions that we're using are, is sigma known? Well, in this case, yes, sigma is known. It's 120.5. So let's put a little check mark there. And the other assumption we could check is we want to know, is n, which is equal to 20, greater than or equal to 30? Well, no, it's not, which means that it fails this. Now, if you remember when we're checking our assumptions to see if we can use a standard normal, one of these must be true. It's an or statement. Sigma must be known, or n must be greater than or equal to 30, or both. So in this case, we're going to use our standard normal. So use z. So the next thing we're going to do, we're going to find our rejection region, which for an alpha of 0.05, for a two-tail test, if you remember, the way we found this is that if alpha is 0.05, that means the area of our rejection region is going to be half of that on each side, so 0.025 and 0.025. And looking at our table, that means we want the z value, if we're using the positive, that has 0.975 below it. So we go to our table, we find where 0.975 is, which is going to be right here, which gives me a value of 1.96. So this value is 1.96, and this makes this negative 1.96. So based on the rejection region, if our test statistic falls below what negative 1.96 or above positive 1.96, we would have enough evidence to reject our null hypothesis. So let's find our test statistic. We're using the z value, right, because we're using standard normal. So our test statistic is going to be z equals x bar minus mu over sigma divided by the square root of n, which is going to be, we're going to plug in our values. 521.5 minus 500. I got this mu from our initial claim of our null hypothesis. Because remember, at this stage, we're saying, assuming that this is true, let's test it out based on our data. Divided by, our sigma is 120.5, divided by the square root of our n, which was 20. And then doing this, we get a value of 0.8. So using our rejection region method, or critical region method, we could see where this falls. Well, it's a positive value, meaning it's to the right of 0, but it's less than 1.96. It would fall somewhere over here, in which case we would fail to reject it. But now what we're going to do is we're going to look at our p-value to see how strong the case was in terms of our alternate hypothesis. So because this is a two-tailed test, I know that I need to take my probability that z is greater than the absolute value of my test statistic, and I need to multiply that by 2. And again, because my table, I'm going to convert this, so this becomes 2 times 1 minus the probability z is less than the absolute value of my test statistic. So my test statistic is 0.8, so this is going to be 2 times 1 minus the probability z is less than 0.8 because it's already positive. And I just have to figure out what is the probability that I get a value that is less than z equals 0.8. So I go down to 0.80, I get 0.7881. This is going to be 2 times 1 minus 0.7881, which is going to end up being 2 times, and this will be 0.2119. So 2 times 0.119, I get 0.4238, right? Because if I did 2 times 9, I would get 18. Bring the 1 over, 2 times 1 is 2, plus the 1 gives me 3, 2 times 1 gives me 2, and then 2 times 2 gives me 4. So we have a probability, or a p-value, of 0.4238, meaning that if we were trying to reject this null hypothesis, the probability of something being as at this value or more extreme is 0.4238, or about a little over a 42% chance of that occurring. That's pretty common, so that's not really evidence to kind of support that we can reject our null hypothesis. For our next example, we have an SAT tutoring center claims that the average math scores of their students on the SAT is 500. Consider a small sample size of 20 students with a sample mean of 480, so we changed that one part of the problem, with a standard deviation of 120.5. At the 5% level of significance, do we have sufficient evidence to prove that the average math score in the SAT are less than 500? So in this case, we've changed a few things, but otherwise it's mostly the same problem. So let's write down our given information. First thing, we still have a small sample size of n equals 20. We have an x bar in this case of 480. And then we have to look at, is our sigma known? Well, in the way it's written is, the sample mean of the scores is 480 with a standard deviation of 120.5. This means that we calculated it, right? Because it's in the same sentence, or the way it's implied, it's not coming from a prior source, such as a previous study or from some company or manufacturer or something like that. So in this case, we're saying that this is S. It came from the actual data. So we have S equals 120.5, and then our alpha is still 0.05. So now we're going to check our assumptions. Is sigma known? Well, no, because we have S, so this fails. Is our n, which is equal to 20, greater than or equal to 30? Well, no, because 20 is less than 30, so this also fails. So because both of our assumptions have failed, this means that we need to use our student's t-distribution. So now, let's figure out what our critical region is for our student t-distribution. So for our student t-distribution, it's still a normal-ish looking distribution, which is centered around 0. Now, we're doing a left tail test. So let's write our hypotheses real quick. The initial claim did not change, so mu equals 500. But we're saying that we think that it's actually less than this, right? It says, do we have sufficient evidence to prove that the average math scores on the SAT are less than 500? So we're going to have our alternate hypothesis. Mu is less than 500. So this means we're doing a left tail test, meaning that we will have some critical value, I'm just going to call it t critical, that is here, which will give us our rejection region. Now to find your rejection region, your t critical value that creates this rejection region, where this is equal to alpha equals 0.05, we're going to go to our student's t table. We are going to go down to our degrees of freedom. So in this case, we have a degrees of freedom of 19. We're going to go on the first row for one tail, and we're going to find 0.05. And then we're going to see where do these two intersect, which is going to be right here at 1.7291. So that is our critical value of t. It means that if we have a value that is below this, right, because it's on the left, this means that it's going to be a negative. If we have a value that is below negative 1.7291, we would have enough evidence to reject our null hypothesis. So let's test it. Our test statistic for t is going to be x bar minus mu over s divided by square root of n. So our x bar is 480. Our mu is still going to be based on this null hypothesis, 500, divided by our s, which is 120.5, divided by the square root of n. And if you kind of look at it, it's the same calculation that we did previously, except for we're using the sample data's standard deviation instead of a population parameter, sigma standard deviation. So this is going to be equal to negative 0.74. So again, using the critical region method, if we were to look at where this falls, it is negative, meaning it's to the left of 0, but it's not beyond negative 1.72. It might be somewhere like here, meaning it falls in our fail to reject region. So right now we can already tell you that we fail to reject, but let's do p-value to see how badly we fail to reject this hypothesis. So now we're going to go to our t-table. We're going to go to our degrees of freedom, 19, and we're going to find where the absolute value of this value, so this is negative 0.74, we're going to find where positive 0.74 falls. So 0.74 is going to fall right in this first interval. And then I'm going to go up to the top row, which is for one tail, and I get 0.2500 and 0.1250. So again, I'm going to flip those. I get 0.1250 is less than p is less than 0.2500. So it's between 0.125 and 0.25. Now comparing this to our alpha of 0.05, every one of these values is larger than 0.05. So this means that, again, this agrees that we would fail to reject our null hypothesis. And then we would state the conclusion, which would be at the 5% level, or 0.05 level of significance, we have insufficient evidence to reject our null hypothesis. Now, one thing I want to talk about real quick while I have you here is what do you do if you get a value that falls beyond what's on this table? Well, it depends on the direction, because if you have a value that is beyond the right side of the table, meaning it goes beyond what we have here, in this case, you would just use, whether it's one or two tail, you would just say that it has to be something smaller than one of whatever value you land on. So for example, if I'm doing a one tail test, I have the value 0.0005. So I would say that my p-value is something less than 0.005, because remember, it's going in descending order. If I'm doing a two-tail test, I would have to say that it's less than 0.001. If I have a value that is beyond my table on the left side, meaning that it's too small even to be in one of these intervals, then I would have to say that it's greater than whatever value based on whether it's one or two tails. So for one tail, I have 0.250, meaning that my p-value is greater than 0.250. If I have two tail, the value is 0.5. I would have to say that the p-value is greater than 0.5. So it's still an interval. It's just instead of it being an interval between two values, it just sort of says it's either below or above this value. As we kind of wrap up looking at a hypothesis test for a single parameter mu, I wanted to just add a little bit more because it's not really worth making its own video for. So the first is that if we wanted to use the third method, which is the confidence interval method works just like when we were finding a confidence interval, right? If we have some standard normal or student t-distribution, we have some interval that is our confidence interval. And we're saying that we're some percent confident the true mean falls in here. So when you find your confidence interval, remember the fact that c is just equal to 1 minus alpha. And alpha is 1 minus c, because alpha plus c is just equal to 1, right? The area under the curve is equal to 1. So when I find these z critical values that give me this confidence interval on the standard normal, then really what I'm doing is I'm telling it half of my alpha is to the left, half of my alpha is to the right. Meaning that if I have a two-tail test, instead, if I have a confidence interval, I could just look at the fact of if my value falls in the confidence interval, then I fail to reject the null hypothesis. If my value falls outside of the confidence interval, then I would reject my null hypothesis. The problem lies that if we were to apply this to a one-tail test, let's say that we're doing a left-tail test. Well, I find this confidence interval, right? Well, remember that this is splitting it by alpha over 2 and alpha over 2. So when I'm doing a left tail test, though, I know that my rejection region should be alpha, not alpha over 2, meaning that my rejection region on the left is too small. This means that there's a region here where the confidence interval method would say fail to reject. But the critical region method would say, no, we should reject this. Also, if I end up with any values here on the right, these also would fall in the confidence interval's rejection region. So you have to be very careful when using a confidence interval method, which is why a lot of times you see my slides, I basically have them grayed out, because if you have other options, there's almost no reason you'd ever choose this unless you were doing a two-tail test and you happen to already have your confidence interval calculated. So then in conclusion, we had 3 different ways of doing a hypothesis test. The first is using our critical region method, where with our null hypothesis at the center of our distribution, we have 2 critical values if it's 2-tailed test, or 1 critical value depending on if it's left or right tail test, and anything that falls beyond that critical value falls into our rejection region. If it falls inside or to the fail to reject side, then we would have insufficient evidence to reject the null hypothesis. If it falls outside that rejection, that critical value, then it falls into a rejection region. We have enough evidence to reject our null hypothesis at whatever level of significance we chose. Our second method was looking at the p-value. If we have a p-value that is less than or equal to alpha, we have enough evidence to reject the null hypothesis. If our p-value is greater than alpha, we have insufficient evidence to reject our null hypothesis. And then third method is if we have a confidence interval and our value falls inside the confidence interval, then we fail to reject the null hypothesis. If it falls outside of the confidence interval, then we have enough evidence to reject the null hypothesis. But again, be careful, because if you're doing a 1-tailed test, there's a lot of places this can go wrong. If it's 2-tailed test, it's analogous to doing the critical region method. Once we've done our hypothesis test, then we usually want to state what the conclusion is. So if we have enough evidence or we're rejecting the null hypothesis, we would just usually say at the blank level of significance, we have sufficient evidence to reject the null hypothesis. If we fail to reject the null hypothesis, we would say at the blank level of significance, we have insufficient evidence to reject the null hypothesis. Now, you don't have to say it exactly like this. We usually just teach our class like this so that it's kind of cookie cutter so they know what to write. But in the end, the important parts are whether you're rejecting or failing to reject and at what level of significance. Because remember, if I change the level of significance, your conclusion might change with it. Last thing is, if we have sufficient evidence to reject the null hypothesis, we would say this test is significant. If we have insufficient evidence to reject our null hypothesis, we would say that this test is insignificant. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.